having just finished a discussion of the rates of chemical reactions and analysis of the rates of chemical reactions, we now turn to another topic, and that is what happens when those reactions come to completion. What happens when there is no further change? And that is a very important concept in chemistry, and that's the concept of equilibrium. So what happens when a reaction no longer changes, the concentrations. First, we'll introduce some concepts, and that situation is called equilibrium. So many reactions, and in fact most reactions, are reversible. That is, even though we've discussed reactions as if they're one-way processes, reactants go to products, the reverse reaction of most of these reactions can also take place. We can start with the products and we can go to the reactants. And whether we do that depends on the conditions. But ordinarily, both reactions can take place. And so the reactions are said to be reversible. A reaction will go until, well, if we're observing concentrations, what we will see is that the forward reaction will go, and then the reverse reaction will go, and they will both be taking place until we reach a point where the rate at which products are being produced is the same as the rate at which those products are being used up in the reverse reaction. And at that point, there is no further change in concentration. That situation is called equilibrium, or chemical equilibrium. The reactants and products are both present, so we haven't used up all our reactant, and the concentrations are constant. Now, something to emphasize here, even though we say constant concentration, doesn't really mean the reactions have stopped. It simply means that both reactions are occurring forward and reverse, but they're occurring at the same rate. In that way, we say that equilibrium, chemical equilibrium, is dynamic. It's not static. Both reactions are still occurring. These graphs introduce the concept of equilibrium. So the reaction isn't written here, but basically what we have is this molecule, N2O4. N2O4, notice we start with a certain concentration of N2O4, and with time it splits into two molecules of NO2. So if we make a graph of the concentration of N2O4 with time, we see initially it decreases, just like the first and second order decays we discussed. And we start out here with initially at time 0 with no concentration of NO2, and we see that with time it is increasing, as I'm showing here. So anyway, as the reaction takes place, with time the rate at which N2O4 is being used up levels off, and it eventually levels off to some constant concentration. Notice the concentration is not 0, unlike the decays that we discussed before. Those were reactions that went to completion. And it's not 0 because the reverse reaction, where NO2 is going to N2O4, is also taking place. And we eventually reach a point where the reverse reaction and the forward reaction are taking place at the same rate, and we can see that at this time, indicated here, there is no further change in concentration, and we've reached equilibrium. And these concentrations indicated here are the equilibrium concentrations. So as the system approaches equilibrium, both the forward and reverse reactions are occurring. Once equilibrium is reached, the amount of each reactant and product remains constant, as you see beyond the time at this dotted line. If you graph the rates of reactions, the forward reaction and the reverse reaction, over here, notice we start out with a high rate of forward reaction because there's a lot of N2O4 present. And then with time, that levels off because some of the N2O4 is being used up. The forward reaction starts out, the reverse reaction rather, starts out not being, with nothing being produced, and then it rises with time as the NO2 is being produced, and so the NO2 being produced results in the reverse reaction taking place. I get to a certain point here, this is that same equilibrium time right there, where both rates are occurring at the same, both forward and reverse reactions are occurring at the same rate. So notice the lines converge at this point, at this rate, and at that point we've achieved equilibrium. A little about notation. The reaction, when we write the equation for reversible reaction, we understand that both the forward and reverse reactions are taking place. And so we write a reaction with a double arrow as shown here. So the reaction that we were just looking at, we have N2O4 going to 2NO2, it goes in this direction. And then at the same time, we have, if we have NO2 present, we're going to have this reaction taking place. We indicate that with the double arrow. Now, this gets to how equilibrium is related to the chemical kinetics, where we study the rates of reaction. So first we consider the forward reaction. In this case, it happens that the forward reaction is first order. For the reaction to take place, an N2O4 molecule somehow decides on its own at random whether it's going to split into two NO2 molecules. If you recall, that is kind of the recipe for a first order reaction within a particular period of time. Any particular N2O4 molecule has a certain percentage chance of reacting. Therefore, the rate is this, given by this KF. F stands for forward. K is the KF is the rate constant. It's first order. It's simply proportional to N2O4 to the first power. So first power is not the number 1 as an exponent is not ordinarily expressed. Okay, so consider the reverse reaction. The reverse reaction requires two NO2 molecules to come together, and if they come together in the right configuration, they will form an N2O4 molecule. So the reverse reaction we write this way. If a reaction requires two molecules to come together, then the rate is proportional to the square of the concentration, or that's actually a second order reaction. So we write the rate law for the second order reaction is Kr, R stands for reverse, and times the concentration of NO2 to the second power. So it's a second order reaction. Now, how is this related to equilibrium? Well, at equilibrium, the forward reaction and the reverse reaction occur at the same rate. So that means the forward rate is equal to the reverse rate. And from the expressions that we have written, we have Kf. This was the forward rate, first order in N2O4. This is the reverse rate, second order in NO2. And those two are equal at equilibrium. And that's the key thing to emphasize is that's at equilibrium. Before I get to equilibrium, those concentrations and rates could be anything. So if I just simply, I can rewrite this equation in this form here, and I see that if I take And you can easily do algebraic manipulation. You can take NO2 squared divided by N2O4 is equal to Kf over Kr, a constant which does not depend on concentration. And that's key. That constant is called the equilibrium constant. And the equilibrium constant is commonly designated K, and sometimes it's as written here. Sometimes we put subscripts on it to indicate various things, but that's capital K as opposed to small k for the equilibrium for the rates. And this one has K EQ, meaning equilibrium. So in general, the equilibrium for a reaction can be written in terms of concentrations. There's something called an equilibrium constant, where it's written as concentrations of products divided by concentrations of reactants. And here's another example. This is the Haber process for, it's a common way of producing ammonia. And here N2, nitrogen gas, reacts with 3 moles of H2 to produce 2 moles of NH3. Now, the expression for the equilibrium constant, and this is a kind of a general way of writing this, the equilibrium constant is some number at some number. It isn't, the number isn't given here, which depends on these concentrations. And the way we write it is the concentrations of products in the numerator, concentrations of reactants in the denominator. Each concentration is raised to the power of the stoichiometric coefficient. So it's NH3 squared. 3H2. That is so 3H2. The 3 leads to H2 to the 3rd power. So this leads to this general expression for the equilibrium constant for this reaction. In the next presentation, we're going to go into expressions for equilibrium constants in more generality. So basically the equilibrium constant, this is the expression for the equilibrium constant I've written here, depends on the stoichiometry of the reaction.